Welcome, everybody. This is C++ features you might not know. And who here has attended the quiz yesterday evening? It was a lot of fun. Just to give you some baselines for the expectations of this talk, I've presented some YouTube comments when I gave it before. So this person liked it. This person didn't like some of the features I presented. This person put it more strongly. And yeah, so look out for X, but this might not be something that you can really use in your day job, or if you want to lose your day job. So there's a reason you don't know these features. So, but it's really useful for quizzes and stuff like that. So let's begin. This is a classic. We've got an array. We can index into that array and assign it. However, according to the standard, array index on a raw array like that is defined to be exactly equivalent to arithmetic and pointer dereference. And the addition is commutative. So you might as well write that. And if you apply the definition backwards, you end up with that. This does all 4 lines do the exact same thing, just a bit weirder syntax there at the end. If you have stood array, note that this one does not work, because here the array access is equivalent to calling the member function. And this is a compiler error, sadly, because there is no member function dot operator that takes a stood array on 17. So raw arrays are much better than stood array. I never like code like that. So we've got 2 variables, one initialized to 1, one initialized to -1. This is misaligned. Luckily, we can fix that and just write +1. And the plus isn't actually part of the number syntax. This is an operator just like -1. So we can use it. The standard says that it requires arithmetic type and returns the value of the argument unchanged. So it does nothing. However, it changes the type. It does integral promotion on the type. What this means is, if you have an unsigned short s and we write +s, the result will be an int. This is because whenever we have an integer type that is smaller than int, we will just get an int. So you cannot do any arithmetic on short, you will always do arithmetic on int. So if you write +s, the type will change to an int, but the value will remain unchanged. If you have an enum, you will trigger like the conversion to the underlying integer type, so +a will be an int. And if you have an array, you will trigger a pointer to array decay and return the pointer to the first element. This is a lambda. A lambda that doesn't capture anything is implicitly convertible to a function pointer, and if we write plus, we will trigger that conversion to the function pointer. So how can we use this operator? Well, we can convert an unscoped enum to its underlying type, but they're stood to underlying since, I believe, C++ 17 or 20. We can convert an array to a pointer, but that's implicit. We can convert a lambda to a function pointer. And the last one's actually useful. For example, here we've got a type, the template, that takes a function pointer, and we cannot directly give it a lambda, but we can write plus and then give it a lambda, and this will trigger the conversion, and we will be able to just pass in a lambda to a template parameter in C++ 11. In C++ 20, we don't need it. We can just use an auto template parameter and can pass the lambda that directly due to the generalization of template parameters. So, but maybe if you're writing free C++ 20 code, this trick can be useful. Speaking of weird operators, this is the comma operator. And by this, I mean in the end of the for loop, the comma between plus left and minus right, that's the comma operator. All other commas in the slide are just commas. So what does the comma operator do? And this is sort of like the main motivation for the comma operator. It essentially, you have 2 expressions separated by a comma, and we will evaluate the left expression, then discard its value, and then evaluate the right expression and return the value. So it's just a way to put multiple expressions into one place where we would normally only have one. Like the increment and fold. Like we can put multiple expressions in there separated using the comma operator. This is a bit esoteric, but since C++ 17, we were able to do fold expressions, and then the comma operator is really useful. So this function takes a function and a parameter pack, and it will invoke that function on each element of the parameter pack using the comma operator. And because the comma operator has like defined evaluation order, this will be invoked in order. So this will invoke the function on the first element, then the second, and then the third, and so on. There are a bunch of tricks about fold expressions. I've blogged about them. You don't need to copy the URL. All links are also at the end. So that is definitely a useful trick. Operators can be overloaded. And normally you will overload operators like assignment or comparison. Note that since C++ 20, we don't need to overload overload not equals ever again, because it is implicit. The compiler will just do the rewrite for you. This is my favorite feature of C++20. Just stop writing operator not equals, just great. You can also write the overload the space job operators in C++20. You can have dereference operators if you're writing an iterator or something like that, or a smart pointer, and arithmetic operators. This is normal overloading. However, we can also overload more operators. Like a classic is we can, if you have a custom bool, we can overload logical AND and logical OR. However, those ones do not short circuit. So it's usually recommended to never overload those operators because you will use this short circuit behavior that is expected. However, the C++26 standard library will have overloaded operators for those in SIMD. So a SIMD of T is just essentially an array of T's. And then we can do member-wise operations on them. For example, we can do a member-wise comparison. And this will return a SIMD mask, and this is essentially an array of bool. So we have two arrays of ints, for example, we can compare them, and we get back an array of bool, where like each index does like the element-wise comparison. And then we can do a logical AND on those. And this will just do an element-wise logical AND, and it's fine that this one doesn't do short circuit, because there isn't a lot you can do to short circuit, because you want to do like compare each one anyway. So it's a perfect fine way to use overload logical AND and logical OR and so. We can also overload the comma operator. This one is particularly nice if you combine it with custom iterators. So if you overload the comma operator for your iterator, you will catch a standard library that uses a for loop where it does multiple increments to your iterator, and then you get a nice output. So if you want to annoy your standard library implementers, try that, see whether they will invoke the comma operator, which they shouldn't, and then you can file a bug report and annoy them. Like the MSVC standard library is pretty robust against it. It casts everything to void to prevent calling user-defined comma operators, but you might be able to find some other generic code that doesn't do it. See what happens. We can also overload that operator. So what the hell is that operator? This is related to member pointers. So if you have a member pointer, you can write object.star to dereference the member pointer, or a pointer to object arrow star to dereference the member pointer. And just like with the regular arrow operators, the dot version cannot be overloaded, but we can overload the arrow one. So for example, when you have a smart pointer, like unique pointer, you can use arrow star to dereference the member pointer, except this one doesn't compile because nobody bothered to actually overload the arrow star operator. You have to dereference the smart pointer and then use dot star. And I guess like this is a defect in the standard library that you can't do that directly with a smart pointer. Like there's no reason why this shouldn't work. They can implement it, but it's also like nobody noticed it, I guess. Right? I've actually found a use case for that operator in our code base. So I work at ThinkCell. We have used C++ extensively, and we have got like a scope exit macro. So this takes an expression and will execute it at scope exit. And the basic implementation you can do is quite simple. So we just have a struct that invokes inherits from a function and just invokes it on scope exit. And then we just create a variable of that type, give it the lambda, wrap the expression in a lambda, pass that to the thing, and it will just invoke. This will just work, and it can use like so. So you've got a handle to a file, and then a scope exit, you want to close the handle. And it just works. However, the syntax isn't quite nice. What would be a nicer syntax? A code like that. So it's scope exit, and then you've got a block, and then you can put some statements in there. And this almost looks like a language feature, right? This is a defer statement, essentially. And we can do that. We can have scope exit is a macro that expands to something. So we need to create a variable, and then we can use the braces to create a lambda, and then we need to put something in front. And this something can we create like a tag type, and then we use a binary operator. And when we have the tag type and the binary operator, this will then create our scope exit object that will invoke the lambda. So in the middle, we need a overloadable binary operator with high precedence, just so that there's no way to mess it up if you put other expressions at the end. And if you look at the operator precedence table, right there, we've got the arrow star operator and line 4. This is the first binary operator that we can overload. So we can use that here. I will leave this table up. It will become important later in the talk. So just give you some moments to remember the content. There will be a quiz. Okay, I've cut it. There are a bunch more operators, but they didn't fit on slide. So This is the implementation. So we've got our tag type that overloads the error star operator that takes the function on the right-hand side. And then we can define our macro to invoke that. And this will then take the lambda, wrap it into the scope exit input, returns it, stores in a variable, and this will then be invoked in scope exit. And that way we essentially written the first statement, just using a bit of creative operator overloading and macros. So this was almost too useful, so let's talk about else if. Else if doesn't actually exist. And this is the grammar. For if statements, we've got an if, and we've got an if else. There is no else if. But you can write else if, right? So what's actually going on here? What's actually going on here is that the else if is actually an else whose body is another if else. So if you put in braces everywhere, this is equivalent to that. So we've got an if else, and the else itself is another if else. And it's just convention that we sort of treat it as if it were a single statement, like we just combine the braces. If you have guidelines that require braces around every statement, you're not following them consistently because you're not putting braces here, right? So we give else if the special treatment, but why stop at else if? This is an else switch. This is the exact same thing. We just don't write it for some reason, right? But it's really beautiful, like Kunitz-Vetter matching when we've got the else switch. We all do. But switch itself is a lot of fun. So this is switch with multiple cases, a default, fall through, all the nice stuff. First thing, the order of the cases and the default doesn't matter at all. So we can put the default in front. Looks a bit weird, does the exact same thing, order doesn't matter. The grammar also allows for stuff like that. So this is a switch, and it begins with a statement. And because this statement is not preceded by any case or default, it will never be executed. It's essentially like a comment we've put in there for later. And that one actually has a use. So you're constantly writing functions like that because you do not have a reflection, like convert an enum to a string. And if it's a scoped enum, you have to repeat the name, which is annoying. However, luckily, since C++20, we've got using enum. And this will bring all the names into scope, and then we don't need to remove them. But we don't need to put the using enum in the top there, right? This will make it available throughout the entire function, and we only need them inside the switch. So we can put the statement right there. It doesn't matter that it's never executed, because it doesn't do anything when executed. It will just still affect name lookup in that scope. And by the way, that was the only useful thing the YouTube commenter found of the talk. So here you go, you can now get up and leave. Because this is my next slide. This is a switch. If you have a single statement, you don't need braces. So this is a switch. It has a single statement. And then the second statement there's after the switch. So if I is 1, 2, or 3, we will print it, and then we will print the other thing. And otherwise, we will just do nothing and go immediately to the end. You don't need braces around the switch. You can also sort of combine switch with other control flow. So this is a switch that had a merge conflict with an if else. So we've got a switch. If I is 0, we directly jump to the case and print I is 0. And again, the if condition is never executed because there's no label before that. With that, you can write this classic. So this is how C programmers in the 80s used to write memcopy. This will copy memory from one to the other. And the thing is, we want to copy 8 at a time. But what if it's not divisible by 8? Well, easy. We compute the remainder. We jump directly to the middle of the loop, do the appropriate number of increments. Now it's divisible by 8. We ignore all the cases and just do a loop until we're done. So I guess this was idiomatic code, C code back in the day. All that can also be combined to a macro that we use in our code base. And the coworker that showed me the implementation was really proud. So we've got a macro switch no default. It essentially automatically does a default case that doesn't assert false. And the way it's implemented is using a switch without any braces that begins with a default case that has an if else. So what's going on here? If I is 1, 2, or 3, we will ignore the default case and directly jump to the case. And note that the braces are part of the else. Right? So all the braces are child of the else statement. So we'll directly jump to the appropriate case. However, if we don't hit them, we will hit the default, start executing the if else, and because if true is true, we will directly jump to the assertion. And that way, if we want to have a one-time check that we don't hit the default case, we just write switch no default instead of switch, and it just works. Like as I said, the coworker was really proud when we showed me this macro. The C++ standard library has like fixed size integer types. It also has the same thing for float. So we've got float t and double t. And this is defined to be like the fastest float or double on your system. It usually float and double respectively, but it both could be double. This is the idea behind that. And if you start looking at float stuff in the standard library, especially the C standard library, there's a lot of weird stuff. So we've got these macros that define rounding modes. So we can say that we want to have floating operations be rounded downwards toward negative infinity. Or upwards, always round up. The default is round towards 0, so this will round positive values down, but negative values up. Or we can also do like actual arithmetic rounding, where we'll just round to the nearest value. And then there's this function, if you set round, this sets the current rounding mode. It's a global state, you give it one of those flags, and it will change the rounding mode of certain standard library floating point operations. So we've got these integer rounding functions in the standard library, one for each rounding mode. But if you want to have more global state in your program, you can also use nearby int, and this uses whatever you set in the global variable as the current rounding mode. So if for some reason you want to change the rounding mode in one central place in your program, you can use nearby int, and this will in effect all rounding mode operations. I guess this was useful for something. Important caveat, if you start using this, if you use round on 2.5, what will the result be? So we round 2.5. Will it be rounded? So this rounds to nearest. Is the nearest 2 or is the nearest 3? 3. Okay. And then the other one, and we also round to nearest and use nearby int, and as expected, we print 3 and 2. And this is because std round always on dot 5, it will always round up. But nearby int, with every 2 nearest, it will round to the even integer. So 2.5 will be rounded down to 2, but 3.5 will be rounded up to 4. So I guess now you know. We've also got something called floating point exceptions. So there are 5 of them that happen on various operations that might fail. For example, we can have an overflow when the floating point value is too large, or we can have an underflow, which is when we are too close to 0 that it just turns into 0. So if you want to annoy your coworkers, integer underflow doesn't exist. If you have an integer value that is too negative, that is still integer overflow. Underflow is only when you truncate something down to 0 that is non-zero. So, and before you think exceptions, I know what exceptions are, now you don't. While you have a function to throw an exception, you need to call a function to check whether an exception was thrown. So it's essentially a global flag that is set when an operation occurs, and then you need to frequently check that if you want to react to the exception. So it's part of the C library, they're not really exceptions. The way they can be used is as follows. So we first of all have to clear the global flag, because it's global. Then we do an operation, and then afterwards we can check whether we had a division by 0. Okay. So if we have 1 divided by 0, we will print infinity and say this is a division by 0. What happens if you divide 0 by 0? Who knows what the result of 0 divided by 0 is in floating point operations? None. I hear 9. Yeah, it's almost correct. It's a negative none, actually. And then we still print division by 0. So why is it negative none? Well, nan, just like any other floating point values, has a sign bit. And on Intel CPUs, whenever you create a nan out of an operation, the sign bit is set, so it will be printed as negative nan. But there are a couple more nans, because this is sort of the bit pattern of a nan. The exponents is all 1, then you've got the sign bit, and then the x's, they can be anything. Which means that on a 32-bit float, you've got over 60 million different nans that you can use. So how do you get one of those nans? Well, the standard library provides a function. You give it a payload, which is a string, and it will return a nan that will store that string essentially in the x's. So you can create a very customized nan. And that one is actually really useful. It's called nan boxing. So for example, consider a JavaScript interpreter. It needs to store the current value, which is either a number or a pointer to something. Well, it just turns out that you can put a pointer essentially in the nan bits of a 64-bit float. So you can just need to store all the values are just doubles, and if they are not nan, then they are a number. Otherwise, they are pointer to the actual data. So you can just store everything. Every JavaScript object can fit in a double using nan boxing. Again, link at the end. So, east const versus west const, right? We've got declaration specifiers, const and int, and we can write const int or int const. We can also write const expr explicit or explicit const expr. But for some reason, there is no big divide in the community which one is correct, because I don't think anybody remembers which way they put it. They just write whatever they think at the moment. But both are valid. You can also same with unsigned. You can have like east unsigned or west unsigned. But again, There's market potential here. And in fact, the grammar just says a declaration starts with a sequence of decal specifiers, like int or const or unsigned. And they can be in any order. So you can write that. This A is a type diff for an int. This is a volatile float that is also inline and static. This is east const expr, which what we're actually using in our code base because it's consistent with like const, I guess. I'm not a big fan, but you know. And that one, that is an unsigned long. But the unsigned is in the middle and the longs are split apart by the thread local and the extern. So here's my guideline for my advice for a company coding guideline. Sort all declaration specifiers alphabetically. That way you avoid the east const and west const because you write const int but auto const, right? Just sort them alphabetically, it's valid code. So we've got our decal specifiers, and then we've got what's called the declarator. So here the declarator is name. And the idea here is that they sort of mirror the expression syntax. So when you want a pointer to an int, you write a declarator that is just a star pointer, just like you would have in the expression. Or array 10, and then you do array index. Or a function, you give it a function. So it sort of like mirrors the expression syntax, which was the big philosophy behind C's declaration syntax. Of course, then C++ went ahead and added references, and you don't need to use an ampersand to use a reference. So it sort of broke that philosophy, and now it's just random tokens you put in front of the name, but oh well. Interesting thing, because it mirrors the expression syntax, you also sometimes need parentheses. So the top line is an array of pointers, because if you write star array of pointers index, you will get that way you will get the int. But the second one is a pointer to an array, because likewise when you access it, you first need to dereference, and so you can use parentheses to control what it means. So the grammar allows that. This is a variable the parents of type int, and you just put extra parentheses in there. And of course, by stop at 1, right? This is a function that returns an int and takes no arguments. And of course, this also means that this is not a constructor call or something, but this is a function that takes a variable called c of type b and returns an int, which is why you sometimes need to use curly braces for that. So this is where that comes from. You can just put extra parentheses around anything, and the compiler essentially has a rule that when it could be a declaration, it is a declaration. So this is a function. And not a constructor call. So you can put multiple declarators in a line using commas. So this is two ints a and b. Then we've got a pointer to an int c. And because the star is part of the declarator, not of the decal specifier sequence, this code only has one pointer, a, and b is a regular int, because the star is not part of the type, so to speak. It's part of the name itself. You can initialize variables, so d is now 42. You can also call the default constructor, except, oops, this is a function call, so e is a function, and that takes no arguments and returns an int. So you can just declare functions in the middle of your variables. By stop at 1, f is a function that takes an int and returns an int, and we can just write. So if you want to declare a lot of functions that all return an int, for example, just declare them in one line using commas. I've seen that once, actually, in code my uni professor once wrote to do some parsing stuff. It was surprising. And yeah, then we've got this thing. So I didn't put it in my speaker notes what it is, so now I don't know. It's something like it's a function that returns a function pointer or something. But we can, this is valid syntax. So function pointers, right? Nice syntax. This is a function pointer. This is a function that returns a function pointer, right? So you just need to put parentheses around there, put the star in the middle, and then get an extra argument list at the end for free. This is an array of function pointers. But there's one final place. We've got lambdas. And lambdas are implicitly convertible to function pointers when they don't capture anything. So the compiler will generate something like that. This is a lambda that doesn't capture anything, implicitly convertible to function pointer. Except that's not the correct syntax for a conversion operator to function pointer. Maybe that. So we put extra parentheses, put the star in the middle. So we sort of the name is operator and then the arguments, and then the star means it returns a function pointer. That one isn't right either. Okay, maybe that. Maybe we put the operator in front and just the name is empty and we just have that. So the middle empty, this is the argument list of the conversion operator. But that one isn't right either. So then you get creative and try that. MSVC actually accepts that. but the other compilers look at that and say no. So this is also not the thing. And the reason, there actually is no syntax for a conversion operator to function pointer. You just cannot write the type there. And it's an oversight in the grammar. If you want to write a conversion operator to function pointer, you have to use a type def, or you have to use auto, and then have the compiler figure out what the type is. Right? This is, again, an oversight in the grammar. There is no grammar that allows you to put a function pointer there. Similar thing, you can also can't have a conversion operator to a reference to an array or something. It's just no way to write that in C++. Which, again, is an oversight, but then again, like, it's whatever the syntax is, like, it wouldn't be readable anyway, so just use a type def. Or auto. So we finally managed to get our function pointer, now we want to use it. And correctly, we would write it like so. So we take the address of a function, store it in a function pointer, and then dereference it to get it. However, we don't need to write all this noise, we can just write it like so. So we don't need an ampersand when we get the address of a function, and we don't need a star when we want to call to a function pointer. And this is because of two rules. The first one says there's an implicit conversion from a function to a pointer to a function. So this allows the first line. And then the second rule says that a function call either needs to be a function pointer or a function. So essentially, the compiler will implicitly dereference a function pointer when you call it. So you can get the noise. However, the first rule is interesting. A function type can be implicitly converted to a type pointer to itself. So when we call a function, we might as well write it like that. Right? We can put the star there, because the compiler will implicitly then convert it to the address, we dereference it to get the function back, and then we can call it. And then we can do it again. So again, each time before the star, the compiler will take the address, and raised by 2. We can do it 3 times, or however many times you want. It just implicitly converts, dereference, and so on. So if you want to do extra, I don't know, stars in your program, here you go. This is some code that uses some global declarations. And we don't actually need to put the declarations of the global variables at global scope. We can put them inside the function. And this does the exact same thing. Because int global is marked as extern, it is still like a statically linked, has static lifetime, it's not a local variable, and functions are implicitly extern, so this will just work. So this is because there is no link between the visibility of a name and the linkage and lifetime and so on. So there is no difference between this code and that code, except now the names are not visible outside of f, and if you wanted to call them, you have to declare them again. But this is allowed, you can just put them inside for greater encapsulation or something. And this also means that people always say that static has so many meanings. This is true in C++, but it is not true in C. Because in C, the only difference between a static at file scope and a static at function scope is the visibility of the declaration. Static just means this thing has internal linkage and static storage duration. And whether we put it outside the function or inside the function doesn't make any difference. Right? So static just means one thing, and the rest is just a consequence of other language features. And this is because, unlike in C++, the initializer of a static has to be like a constant expression. So both variables are always initialized at compile time and not the first time you call the function. So there really is no difference between file statics and function statics in C. It's the same thing. It's just a consequence of other rules. So we've got a main function. A main function has a try catch. And this is a comment pattern. You have some code, and then you want to catch an exception and log an error. You can sort of write it a bit more compactly using a function try block. So essentially, you sort of get rid of the outer parentheses, outer braces, and just write it like so. So you've got a main, and then you immediately got a try with the try block, and then you got catch blocks at the end of the function. And that way you can save a bit of time when you want to write a main that essentially tries everything. The motivation for this feature actually member initializers list. So what to do if a member initializer throws, how do you catch that exception, right? There's no scope where you can put a try catch block, except a function try catch block. So that way you can catch an exception caught in a member initializer list and still react to it. This is sort of like, it's a bit of a weird syntax, but it's a bit of a special case. So we've got struct and we've got class. And the only difference is the visibility, right? In a struct, everything is public, and in a class, everything is private. But there are a couple of more places where you can use the keyword class. So for example, you've got an enum class. You can also write an enum struct. And they mean the exact same thing. It's just that the grammar just allows the keyword class or the keyword struct. So you can mean the exact same thing, no difference. You can pick either one. You have template parameters. You can have a type name T, or you can have a class T. What about template struct T? So is that legal code? We've got a template that takes a struct T, like similar as it did the class T. Is that allowed? Who thinks that is legal code? Okay, well, the majority thinks this is a trick question and don't want to answer, I think. This is in fact legal code, but it is also a trick question because this doesn't do what you think it does. The way you instantiate the template is you give it an object of type T, of course. So the struct T is an unnamed non-type template parameter of type struct T. It does not get a type. It gets an object of type T. And so if you want to instantiate it, you have to give it an object of type T. And this only happens with struct. If you have a class, this is still, you give it a type. But if you write struct T, this is a non-type template parameter of type T. Right? There's a name missing in there. It's just, somebody pointed out to me when I told them that I'm giving a talk about C++ features you might not know, and they were like, oh, you try out struct T in a template. Yeah. So if you want to really confuse people how to use your template, this is the way to go. When you've got classes, you can build a class hierarchy. And then you can use dynamic cast to do casts in that class hierarchy. For example, with dynamic cast, you can do a check down cast to check whether we really have a derived class. You can also do what's called a sidecast. So you've got derived that has two bases, base 1 and base 2. And you've got a pointer to base 1, and you want to get a pointer to base 2. And then you can use a dynamic cast, and it will sort of go down to derived and then back up to base 2. And again, this is checked only if you really have a derived object. So this is a checked sidecast. And there's a third use for dynamic cast, a dynamic cast to void star. And what this one does, it gets you the address of the mouse drive type. So here again, same deal. We've got two base classes and then a derived class that inherits from both of them. And we've got a pointer to base 2. And we want to get a pointer to the beginning of the derived object. So like the pointer to base 2, it points in the middle of the object. And we want to get a pointer to the actual derived object. And then we can use dynamic cast to void star, which gives us essentially the same address as the entire object. So it will just offset the pointer to the appropriate place. And of course, it has to return a void star because the type has to be known at compile time, but like the dynamic type of the thing is known at runtime. So the best it can give you the address, and then you need something else to know how to cast that to the appropriate type. So this one is really niche feature, but it can be useful in cases like, for example, we've got std any in the standard library, which owns any object of type T, and you may want to have an anyref, which is a pointer to any object. You can construct it directly from a reference, and then you will just take the address and get type ID to have the type of the thing. But you can also give it like a base class reference, and then you want to type ID just works. But if you want to store the address, you cannot just take the address of base because this might be in the middle of an object. And then you do a downcast and to the thing not on the initial address, but like of a sub object, and this will just break. So you have to use dynamic cast to void star, and this will give you the actual address of the dynamic object at that point. It's a really niche situation, but if you know about it, it can be useful. So if you don't want to use any, you might want to use union. So this is a union. We want to sort of windowing events, right? So we've got an event kind, and then we've got various payload. So for a keyboard event, it's the key code we've clicked on, and so on. And the size of this thing is the size of 3 uint32s, because we've got a uint8, and then each payload are 2 uint32s, but we need to have padding between the uint8 and the union. So we've got like 3 bytes of padding in the middle. And this is a bit frustrating for me. I like to pack my types tightly, and like there is enough space in the payload to also store the event kind. So I somehow want to get rid of the padding. And one way to do it is to store the event kind not outside of the union, but inside of each union member. So then we can tightly pack it inside the payload and don't need the padding. And we can do that because of a quirk about union access rules. So in standard C++, you're only allowed to access the union member that is currently active. But there's one exception. And that exception has to do when you have, when you want to read a member of the active union member that is also present in another union member. There's standards, I put it on there, it's a bit convoluted. It talks about the common initial sequence, which is just a sequence of members and so on that are layout compatible. Details don't matter. What the end effect is that you've got a union where each alternative starts with the event kind. And then you can access the event kind through any union member, regardless of which one is active, because everyone has it, right? So you can just write mouseclick.kind, even though you're a keyboard event. You can write keyboard.kind, even though you're a mouse event. Or you can just write union.kind, because it's also in there, right? It's the same member in everyone, and you're allowed to read it through every alternative. And that way, you can you get rid of the padding, essentially. You can pack your union more closely, because you don't need the padding bytes by inlining this thing. So if you've got this pattern in the code base of a union, of essentially like an enum tag and then some payload, consider whether you might be able to move the enum tag into the payload, as long as you do it in the same place in every member, like it has to be the first member and everything for the trick to work, obviously. Then you're able to do that, and this is completely well-formed C++ code, no issues here. This trick can also be used to do something really cool. So we have a type that doesn't have a default constructor. It's an empty type without a default constructor. And then we can write this function legally create object that returns an object of that type. Even though the type doesn't have a default constructor or any other constructor, we are allowed to legally create an object. And this was really useful back in the day, I think before C++20, where captureless lambdas didn't have a default constructor. But they're captureless, so they should have one. So they're empty types, so you can legally create them. And the trick, Louis gave a lightning talk at C++ Now about it. Essentially, the trick revolves the fact that if you have an empty type, it doesn't affect the common initial sequence of the union. So you put it in the union with something else, construct another alternative you're allowed to construct, then read it through the other alternative, and it's a beautiful trick. Again, watch the lightning talk link at the end. And while we're at unions, unions can be private, they can have member functions, they can have constructors, they can have destructors, just like any other class. So this is a union with private members and member functions and all the other thing. So this is completely allowed. Now the standard library has a couple of dynamically sized containers: vector, dec, list, forward list. We've also got vector bool, which is different from vector t, for annoying reasons. And then we've got Valarray. Now, Valarray is an interesting container. Valarray is an actual vector, right? You can create Valarray afloat, and then you can do arithmetic on them. Member-wise, similar to the proposed SIMD stuff. You can also use it for matrices, and then you can index them. So this will compute the trace by indexing into the diagonal, and then you've got member by sum and so on. It has a bunch of useful operations. Wide range of mathematical operations. It has overloads for sine and cosine and whatever. They're implicitly restrict, so if you pass 2 by reference to a function, the compiler is allowed to assume that they don't alias to do more optimizations. It can use expression templates to do like fused multiply adds and so on. So it's a pretty nifty type, but nobody uses it. It's been in the standard library since '98, and it's sort of been forgotten about. And because it's forgotten about, the standard library vendors don't spend time optimizing it. So it's not sort of like chicken and the egg problem. Nobody uses it, so they're not optimized, and because it's not optimized, nobody uses it. But it's there. Like in principle, if you want to do like math on dynamically sized vectors, right? This is like a baseline, a pretty easy thing right there. Just include the header. The standard library also has exceptions. This is std runtime error. This is the full interface of std runtime error. And then you can use it by throwing it and formatting a message in there. Now, notice anything odd about the interface of std runtime? In the fail function, we're giving it a std string. So we're invoking the first constructor. And because the string is a temporary, like runtime error has to store that string somewhere. Yet the copy constructor is no except. So where's the string actually stored that the copy doesn't involve dynamic heap allocation and is no except? And the answer for that is std runtime error is a ref counted string. So when you copy it, you don't copy the string, you just copy a ref count. It's essentially like a shared pointer of a string, like an immutable shared pointer of a string. So if you need a ref count string in your application, here you go. The interface is a bit weird, so I propose you use a bit of a wrapper class. But here we go, easy ref counter string in 5 lines of code. Of course, you might want to use exceptions. And for that, so this is code that uses exceptions using a function try block or the nice thing, but you might want to use exceptions for performance reasons. And because an exception is essentially go-to, right? So when you throw an exception, you want to go to the catch block. So let's try using goto. So we want to go to the catch block. That one doesn't work because you cannot use goto to jump to another function. You have to use long jump. So long jump, something of the C standard library. You need a global variable to store the label. That's the first nice thing. And then in main, you call set jump. And this will remember the current position and store it in the label. And then it will return 0. And when it returns 0, you can do your actual work. You can call compute, and if there's an error, you use long jump. And you give it a label and some payload. This has to be non-zero. Well, if it is 0, it will just be turned into 1. So just give it a number. And what this means is it will jump to the label, to the address stored in the label, which is the setJump call. And now setJump will return the number that you gave it. So on the second time, when setJump returns, because it's a function that returns twice, it will return 1, and we will enter the cleanup phase. So this is essentially exceptions without using exceptions, but just by using goto to another function. And in fact, like early exception implementations were implemented on top of setJump. The only thing you need to do is you need to ensure that the destructors are called and you've got proper exceptions. Because this one will not call destructors, it just directly jump to the setJump. And the implementation is actually pretty cool if you're interested in that. So essentially, setJump just needs to save the current execution registers, and then longjump just restores them, and the CPU will continue in the new state. Again, at the end, there's a blog post that talks about the implementation using assembly and so on. So if you're interested in that, I found it pretty cool. So this is a function that takes 2 ints, and it will do addition on them. Does this function have any undefined behavior? That's not just a question. I mean, the title is right there on the top of the slide. So yes, this can have integer overflow. What about multiplication? Yeah, same thing. And Sean Parent actually calculated it. And there's overflow on 99.99993% of all possible inputs you can give to the function. Because there are not that many ints that multiplied still fit in an int. So essentially, this function basically always does UB, right? If you give it just something, it will be UB, makes it easier to do analysis. What about division? Is there undefined behavior in division? Yeah, divide by 0. B is non-zero. Is there undefined behavior in this function? Yes, there is. Because of 2's complement. So in 2's complement, positive values start with a 0, and then we've got some bits, and negative values start with a 1. What about 0 itself? Well, 0 is stored as all zeros, which means that we have more negative values than positive values. Right? So 8-bit goes down to -28, but up only to 127, because the 0 pattern is positive. So we've got 1 more negative value. This means that int min divided by -1 is integer overflow, because the result would be negative int min, but that is 1 more than int max. So we will have integer overflow using division, but only those combination of inputs. Everything else is fine, but those ones are integer overflow. I mean, in practice, it's a bad thing to say about UB, but in practice, int min divided by -1 will just stay int min, which is a fun property to have. Okay, division has a cousin, modulo, A modulo B. Is there undefined behavior there? Well, yes, there is. Int min modulo -1 is integer overflow. Even though int min modulo -1 is 0, because int min is divisible by -1. So what's going on here? Well, it's UB because the standard says so. If the result is representable of division, then this is the behavior. Otherwise, both A and B and A modulo B are undefined behavior. So if division is undefined behavior, modulo is as well. And this is a good reason. The standard just didn't put it just in there just to annoy you. This is because, for example, on Intel, when you want to do a division, you compute both division and modulo, and then just read different results from different registers. So, of course, if division has an integer overflow, then modulo does the same. So it also has to be undefined behavior. And on ARM, it's even more obvious because, well, not if you read the assembly, but if you read the pseudocode, ARM doesn't have modulo. So it does the division and then computes the remainder. So if the division already triggers undefined behavior, then the modulo does as well. So int min modulo -1, even though the result would be 0, and there's everything's fine, because int min divided by -1 would be undefined behavior, so is modulo. And again, this is only this combination of inputs triggers undefined behavior. It's pretty fun if you want to debug it. then you look at LLDB, and then LLDB says we've got a floating point exception, which is a weird name, integer division by 0, which is not at all what we're doing. We're doing modulo int min modulo -1. So this is a bit confusing. So I told you there was going to be a quiz at the end. So I'm going to show you my favorite C++ quiz. This is a tweet by Richard Smith. Quiz time. We are assuming an LP64 or LLP64 system. What does this print? Think about it for a moment. I told you everything you needed to know to understand this in this talk. So just give you a moment, think about it. What will this code print? Okay, I've heard somebody is ready, so let's go through it. So we've got a string literal. String literals have type const array integer. A is a short. Unary plus there's integer promotion, remember? So the result is going to be an int. Size of returns a size t. The standard doesn't give a lot of guarantees. It says the size of char is 1, regardless of the actual bit width of char. Otherwise, it's implementation defined. However, Richard told us we are on LP64, and their size of int is equal to 4. So we are using the built-in array index operator because the right-hand side is a char array. This is commutative, so we can swap it around. 4 indexed, because that's the result of size of into the string. It's the same thing as swapped around. So the result is 6. And in fact, if you look at the poll results, majority 6, we're good. Just to double check, let's actually run the program and see what it prints. And it prints 1. You didn't remember the operator precedence table I've showed you before. Then we've got subscript, and then we've got size of. Size of is actually a unary operator. It's a unary operator whose precedence is lower than array index. So this code is equivalent to that code, which if you put in parentheses around it, is that code. And the standard says the result of size of applied to any of the character types is 1. So the code was completely portable to begin with, and that he gave us the platform isn't really important. So this is why this is my favorite C++ question. Okay, I've got a bit of time left, so I will annoy you with something that I'm really annoyed by. And sorry about that, I just need to get it out of my system. What is 10 modulo 7? 3. Okay. What is 10 modulo 9 minus 7? I mean, it's still 3, right? 10 divided by -7 is -1, and then you've got a remainder of 3. What is minus 10 divided by 7? Now, here's where it gets interesting. So, this is what the standard guarantees about modulo and division. If you do a modulo b and a divided by b, this formula holds. So a is equal to a divided by b times b plus the remainder. And the absolute value of a modulo b is less than b. So you will not have a remainder that could have fit in b itself. But that gives at least 4 options, depending on how you define division and modulo. You can use truncation. So a divided by b, and then you truncate. That means that you will round the quotient towards 0. The remainder will copy the sign of a, and will be in the interval either 0 to a or a to 0, depending on what the sign of a is. You can use float division, so you always round down towards int min. Then we will have the sign of b. And likewise, so the remainder interval just flips a bit depending on the sign of b. You can do the opposite, round up, and then you will always have the opposite sign of b, which is a bit of an odd choice. And then again, the interval. Or you can do actual rounding. You round to the closest integer, and then the remainder can either be positive or negative, depending on whether you round it up or down. And the interval will be between minus b halves and positive b halves, so it's sort of like symmetric around 0. And except for oh, yeah, and then we've got Euclidean. There you round depending on the sign of b to ensure essentially that the sign is always positive. So a modulo b is always a positive value, which means it will be in the interval 0 to absolute a. And except for bounded and ceiling division, the other 3 are used by different programming languages at different times. And they all make sense. And what this means is C++, just as well, it does truncated division, Lua does float division, and Dart or Haskell or I think Excel also does Euclidean division. For positive values, they all agree. If you do modulo or division by negative values, truncated and Euclidean agrees, but float division, it's less than you expect, because 10 divided by -7 will be -1 plus some remainder, so we will round it down to -2. And that means that the remainder, now you're overshooting, you're now at -14, so you're now at 14, so you have to subtract 4 to get back to 7. The interesting thing is, so -10 divided by 7, in C++, it will be -1 and then -3, just to make it all work out. So you will -10 divided by 7, 7 times -1 is -7, and then you need to subtract another 3. So this is where that came from. And then float and Euclidean division, -2, and then you add 4 to get up. So you overshoot it a bit. And then finally, if both are negative, you've got the missing combination in the table. So now truncated and float agrees, and Euclidean ensures that because the modulo always should be positive, we have to overshoot it and then add something back. And this is like, there is no reason why programming languages should do the same operation differently, but they all picked something different, and now you have to deal with it. It's just like division and modulo by negative numbers. It's just, you have to check your language documentation if you want to do it. Euclidean is really nice. Because this is when you want to tile something, you can use Euclidean division because the result will always be in the appropriate remainder. Truncated is nice because that's what the hardware does, so it's the first one. I don't know why Lua wanted to be special. I think maybe that one is also the one Excel uses. So Excel doesn't use truncated, it uses one of those two. So I don't know. Anyways, this really bugs me. There's a nice table on Wikipedia that lists all the different programming languages and what behavior they have. It's like, yeah. Anyways, so that was my talk about C++ features you might not know. I hope you find the using enum trick useful. If you promise not to use some of those code, we are hiring at Thinksa. We do a lot of C++ code. And also, we've got a booth. We've got a lot of free stuff at the booth. Please go over there just after the talk, grab anything. I don't want to take it all back home with me. So thank you very much. All the URLs links at the that link. Thank you.